So to describe the operations of using OpenFOAM, there have been many people using different steps to do that. Some address more theoretical background, some more addressing the operation software. I want to take care of the both. So by using several parts to address the key behind the key topics or the key skills behind the operation of the software package, because compared to all the user interface software who you may use before, OpenFOAM still like command based, and it may bring some difficulties in the very beginning. So as we know, for any like computer-aided engineering work, the majority of the part will be focusing on generation of the mesh and also the definition of material properties. That is mainly what you should do for the commercial software, and OpenFOAM of course needed to do this as well. So let's see how it works. Just a quick review of the file structure, if you know. So because OpenFOAM is based on a Linux system, so the file is mainly organized in a way that the software can pick up and organize all the problem definitions from you and give you the solutions. So there are three main folders. So 0, constant, and system. So we usually start from system. So because system, it has all the mesh information you generated, and also the controls of your solving process. And the constant is more about the definition of some like geometry. For example, the tri-surface is a geometry that you will use for the mesh generation, and also the mesh will be saved in this folder. So we know the CFD is mainly based on the finite volume method. So the meshes, the points, and the cells information and the boundaries. And the boundaries, I mean, boundaries here is more about the geometric boundaries. So what kind of faces for you in the mesh that can be used as boundary. And then go back, the final one, or the most critical one, is the 0 boundary, which means this all the boundary conditions and the initial definition if it's time relevant at 0. So 0 is mainly about time, so that's a time at 0. So if you have a steady problem, so 0 and the following numbers are really about the steps you are going to do. But if you really have the transient problem, so the 0 and the following numbers are really about your real time. I've mentioned that. So the sequence of solving is to define these files step by step. I suggest starting from system and then followed by constant and final 0. Because the system, we have all the control parameters of your solving process, and there are some like controlling on the solution process as well. So what kind of differential equations going to use, what schemes for that solving process, and also the second step will be the constant. So they are not separated to each other, because when you do some system definition and you really generate the mesh, that will be saved as the constant folder. And the constant folder mainly is about polymesh, which is a folder saving all the cells in the finite volume method. And also the constant is also about the property definition of your material, so the physical properties of material. And finally, to enable the for example, a fixed solution of the problem, you need to define the physical conditions properly, or the solver cannot find the solution, or it goes like divergence and never give you a fixed solution, or it will never stop. So that will be based on the 0 folder about the physical conditions. The physical conditions or physical boundaries really depends on what you are solving. So if you are solving fluid flow, so the main will be the pressure and velocity, for example, for the incompressible flow. But if you include heat transfer, in our case, we will need to define the temperature condition as well. So the theory behind this is about the FVM. So the FVM is about the solution of the Navier-Stokes equations and also the energy equations. So for our problem setting, so go back here. So for our problem setting, so we have the coupled fluid flow and heat transfer, and also the heat transfer between the fluid and solid. So that's why it's called conjugate heat transfer. The solver we are going to use is the CHT multi-region. So that means that it is a CHT but based on the division of the multi-regions. So we have different regions for the solid and fluid. Depending on your problem settings, you can use the transient solver, or you can use the steady solver. So there are two solvers available, and what we are going to do today is really focusing on the steady heat transfer or steady CHT problem. So we will use this, and I also list the tutorials folder for you. So if you want to find some examples more relevant to your questions or to your problem or to your in applications, you can find some good examples from the folders. Of course, the example I present today, I think it is the best because it really covers all the topics of the two main solvers. So there's no difference actually about the definition. Only your problem setting is transient or steady, then you can use the different solvers. And also I summarize one sentence for the CHT definition in OpenFOAM. The key is to split regions properly with region interfaces, and also the independent settings for the different regions. That will be explained in the later stage, and you will understand why or how it means.